A single hailstone the size of a grapefruit takes up to 45 minutes to form, getting hurled up and down inside a thunderstorm so violent it generates winds faster than 200 miles per hour, and the whole time, that hailstone is growing by literally freezing liquid water around itself in layers, like a jawbreaker built from ice and physics and pure atmospheric fury. That's not poetry. That's the actual mechanism. And if you were somehow shrunk down and trapped inside one of those forming hailstones, the way you'd die wouldn't be from cold or pressure. It would be from the ice crystals themselves. Microscopic, geometric, absolutely savage. Here's why that matters beyond just the spectacle. Understanding what happens inside a hailstone means understanding one of the most violent small-scale physics environments on Earth. We're talking about a place where water cycles through states so fast that the rules you learned about freezing, the ones that make it sound calm and orderly, completely fall apart. Let's start with what a hailstone actually is. Most people imagine it's just a frozen raindrop. That's wrong. A hailstone begins as a tiny ice pellet, sometimes as small as a speck of dust. It gets caught in an updraft inside a cumulonimbus thundercloud, a cloud that can tower over 50,000 feet into the sky. That updraft can exceed 100 miles per hour. It launches the ice pellet upward into a zone where temperatures drop to -40 degrees Fahrenheit. Then it falls. Then it gets caught again. Each trip through the cloud adds a new layer of ice. Cut one open and you'll see concentric rings, like a tree trunk. Each ring is one trip through the cloud. Now here's where it gets brutal. There are two completely different kinds of ice that form depending on how fast the water freezes. The first is called rime ice. That's what happens when supercooled water droplets, liquid water that exists below freezing because it hasn't found a surface to crystallize on, slam into the hailstone at high speed. The impact is so fast that the water traps air bubbles before it can organize itself. The result is white, opaque, almost spongy ice. It looks soft. It is anything but. The second type is called clear ice or glaze ice. This happens in slightly warmer regions of the storm where water freezes more slowly. The molecules have time to organize into tight crystalline lattices. Those lattices are transparent, dense, and structured like molecular razors. Now imagine you're 100 micrometers tall, roughly the size of a human hair's width, and you're inside the forming hailstone as a layer of clear ice grows around you. Ice crystals don't grow smoothly. They grow in branching, fractal geometries. The most common shape is hexagonal, because water molecules bond at angles of 120 degrees to each other due to their bent molecular structure. As crystals expand outward from nucleation points, tiny flaws or particles, they shoot out branches called dendrites. These dendrites are sharp at the microscopic scale in a way that makes a razor blade look like a pillow. The growth rate of those dendrites under the right conditions can reach millimeters per second. At the scale we're imagining, that's like a forest of glass spears growing toward you at highway speed. And you can't move, because the pressure differential in a forming hailstone is extraordinary. As each new layer of water freezes, it expands. Water expands by about 9% when it becomes ice. That expansion generates internal pressures that can exceed several atmospheres. The hailstone is actively crushing itself from the inside. You'd be compressed by forces that change direction every time the hailstone enters a new thermal layer in the storm. Then there's the rotation. Hailstones spin as they travel. Some rotate at thousands of revolutions per minute due to the asymmetric airflow around them. At the microscopic scale, that means the crystal lattices growing around you are constantly reorienting. Stress fractures propagate through the ice, then reseal as new water freezes over them. It's a cycle of shattering and rebuilding happening in milliseconds. If this blew your mind, subscribe right now, because we cover science that textbooks were too nervous to make this visceral. Here's the layer that most people never reach. The ice inside a hailstone isn't one crystal. It's millions of individual crystals, each oriented differently, called a polycrystalline structure. The boundaries between those crystals, called grain boundaries, are actually weaker zones where molecular alignment breaks down. Under stress, polycrystalline ice fractures along grain boundaries in patterns that look almost biological, like cracking skin. At 50,000 feet, you're also inside a zone of intense electrostatic charge. Thunderclouds generate their electrical charge partly through the collisions of ice particles. When a large hailstone collides with smaller ice crystals, it strips electrons. The hailstone itself accumulates charge. Researchers measuring electric fields inside severe thunderstorms have recorded values exceeding 100,000 volts per meter. The ice you'd be embedded in is simultaneously a growing crystal matrix, a pressure vessel, and a charged electrode. The electrical discharge through ice creates electrofracture, sudden micro cracks caused by the force of charge redistribution. These cracks propagate at speeds approaching the speed of sound in ice, which is roughly 12,000 feet per second. So what does all of this tell us beyond the visceral thought experiment? It tells us that the interior of a hailstone is one of the most information-rich objects in Earth's atmosphere. Every ring records temperature, updraft speed, and water content at the moment of its formation. Scientists can read a hailstone's life story by analyzing its layers under polarized light, watching the crystal orientations shift and change like chapters in a book written in physics. It also tells us that ice, the thing you put in your drink, the thing children slide on, is capable of extraordinary structural violence when the conditions are right. The same molecular geometry that makes snowflakes beautiful makes the inside of a hailstone a microscopic catastrophe zone. The next time a hailstorm hits and you hear that drumming on your roof, remember, each one of those impacts carries the record of a 45-minute journey through one of the most extreme physics environments on the planet. A small frozen archive of atmospheric chaos, landing in your backyard. If you want more science that makes ordinary things terrifying and extraordinary at the same time, subscribe and hit the bell. We've got episodes on subjects that will permanently change how you see the world around you.